I'm going to use FastMD editor today because I had some trouble with the other one in box. Some of the key combinations do not work properly in box for me. Control insert in particular. So we have this nice macros ready for defining descriptor tables. We might perhaps need a few more constants for the future. Here we see that in addition to interrupt and trap gate that we already have defined, there is also call and task, numbers 4 and 5. Let's use this information. So interrupt gate is 6 and trap gate is 7. We see these numbers encoded here. Colgate is going to be 4. And task gate is 5. We may also define some constants for code that would not be readable and data that would be read-only. If I remember correctly, this is this bit. No, this bit is... yes. This bit is that this is a segment descriptor, this is that this is a code, and it's this bit that defined that the code was readable. And the same bit is for read-only data or writable data. Yeah, this is the second bit. Okay, so we have this basic program working. And we can finally start talking more about protection, as in protected mode, and what it gives us. What we have seen so far is that, for example, this instruction, if we try to access data outside limit of segments, because our segment for data is quite small, in real mode every segment was always 64 kilobytes, and here we can define each segment with its own limit, and the limit can be quite small. When we try to access an address above the limit, an exception occurs. And we see the exception here. Number 13, it's a general protection exception. This is already very nice. It allows program to detect when something goes wrong. Of course, we can set up for program our segments in such way that only what should be writable is writable, only what should be readable is readable, and then as soon as the program tries to make something bad because of a bug, then exception signals that something's wrong. But what about a program that does not play nice like this? What about some malicious program that might want to take over control of the system? Well, obviously, if we have in our descriptor table some segments like this one for IDT, and we need to have such segments in order to be able to manage the tables and modify them when we need to load some new handlers, for example. So then such program could load a selector to such segment and use it, and perhaps modify, perhaps even access GDT data. We quite possibly might have a segment for GDT. So this basic protection is not enough. So what does protected mode provide in order to prevent programs from using segments that they should not be using? Let's take a look at documentation again. In every selector there is something called requested privilege level. And this is not the only place where we see this term privilege level. Alright, I found it. In descriptors, there is also a field called descriptor privilege level. Now, one of the general rules is that you can only use a selector if its requested privilege level is the same as the descriptor privilege level associated with a descriptor corresponding to this selector. There are some exceptions to this rule, otherwise it would not make sense to keep this value in two different places. But the other rule is that a code that is executed, also has some privilege level, and it can only use selectors that have not more privilege than the code that is executed. This allows to set up some system segments to have higher privilege and executed programs to have lower privilege and prevent the programs from using this system segments. Let me write this down. We have requested privilege level in selector, descriptor privilege level in descriptor, and something called current privilege level, a privilege level associated with program, which is in fact equal to RPL of CS selector, currently executed code. We have 4 possible privilege levels. 0 is the highest privilege. 0, or on 2 bits encoded like that. 3 is the lowest privilege. Now, you may have sometimes heard the term ring 0 or ring 3. Originally, Intel documentation always referred to this as a privilege level, well, to this day. But it also has something this kind of illustration, and I believe this type of figure was an inspiration for calling these privilege levels ring 0 or ring 3. What we should remember is that 0 is the highest privilege and 3 is the lowest privilege. So it's the opposite of the numbers increasing. The higher the number, the lower the privilege. And the privilege in selector, it's just in the lowest bits. So we could make this selector use a level 3 for privilege just by adding 3 number to this selector. Let's remove the other source of exceptions and let's see if this works. No, it doesn't work. We have a protection exception even before we started writing the message. So we are not allowed to use this selector. Why? I have already said that earlier. So you might have an idea that this privilege level of selector does not conform to the privilege level of descriptor. So let's take another look at descriptors. These are high bits next to a present bit. So we need to shift by 1, 2, 3, 4, 5 bits up. Let's define some additional constants for this. Now we can modify the data descriptor to be of privilege level 3. And let's see if we can use this selector now. Yes, it works. So we can switch to use a lower privilege selectors here. We can do the same for video. But our program is still privilege level 0. It can still use a level 0 selectors and access level 0 segments. We would need to have CS registers, CS register having a lower privilege. We might just naively perhaps modify this, but this is a trap because there are additional rules for the change of privilege level, change of CPL, that is privilege level of code segment. Let's find out about these rules. We want to jump to a lower privilege. And you can see that when we change segments, a call instruction is only allowed to jump to higher privilege, and in the opposite direction, return instruction may go to lower privilege. Jump is only allowed to transfer control to the same privilege level. This means that when we switched to protected mode, the assumed privilege level of real mode was 0. So we jumped to a selector with privilege 0 and this jump was possible. It is not possible to jump to other privilege level. And since we want to decrease our privilege level, jump to lower privilege, we also cannot do this with call. And even if we wanted to jump to higher, then this would need to be a call through Colgate, but let's leave that for later. So we are only left with return. So perhaps set up return and see what happens. Let's make some additional code descriptor. Code segments for ring 3. Wait, let me switch editors. Let's move our program to a user mode segment. Oh, this is another term I use that is frequently used for ring 3, privilege level 3, ring 3, or user code. Oh, thank you, my mistake. I was not showing. I was not showing the window of editor. Let me revert and do it once more to show you what I'm doing. So I'm adding here another descriptor. For user code with privilege level 3. And I'm going to define a segment for this code. And here we are going to jump to this. And we cannot jump, we need to use return, far return. So push selector. Push address. And return far. And I'm pretty sure this is still not going to work, but let's try it. We have an interesting exception here. Number 12. We have not had this exception before. Let's look it up. This is stack segment overrun or not present. This is interesting because obviously we have something wrong with the stack. On the other hand, exception was handled properly, and exception needs stack to operate. So we might expect a double fault there, but there was no double fault. The exception worked. So now let's go back to documentation, and I'm going to find a bit that explains what happened. Where we were earlier. This is about return instruction, and it says that if CPO changes, the old stack pointer is popped after the return address. This is because a code for any privilege level needs to have a dedicated stack for that privilege level. Because on stack you have return addresses and other important values like that. So code privilege of code segment is closely associated with privilege of the stack, and they need to be the same. And we need to set up also a stack. Let's move this here to separate. Ring-free descriptors. And let's make a stack for user mode. We are not going to use expand down this time. Let's just make a small segment like the other ones we made. A 100 bytes should be enough. Oh, we should do the same for user code. I forgot. But fortunately we had a stack error before this one showed up. No. User code. I have mindlessly replaced not the right word. Okay, we have user code, user stack segments set up. And for return we should prepare a stack pointer too. Great, the message is shown. So this is great news, because it means that a code was executing in ring 3 properly, because this code is now addressed only by ring 3 descriptor. Well, so far we have transferred from ring 0, from level 0 to level 3, not the other way around, because it is much harder the other way around. Let's move these user segments together. And you may have noticed that we had an exception there, because we are now running on level 3, and this is a privileged instruction. This is why we have a protection exception there. We should change it to something not privileged. Just a classic hang jump to itself. No exception now. So we are in ring 3. Now, how to transfer control back to ring 0? We may try to make a Colgate. Why is there a Colgate needed then? You see, Colgate is a special descriptor that contains selector and offset for destination. So when you jump far to a selector that corresponds to Colgate, then the offset that you are jumping to is ignored, because the actual offset is taken from descriptor. This is to make it impossible for a ring 3 program to jump to any offset it wishes, because when you can control what offsets of system code you can jump to, then you can do some fancy stuff. You can jump to exactly the instruction you want to execute in ring 0, and this would allow you to break protection. For this reason, you can only call higher privilege levels through a Colgate, and then you have no control over the offset because the offset is stored inside the gate. Okay, there is additional consideration that any change of CPL changes the stack. We already know that level of stack needs to be the same as level of code. In case of return, the previous stack of the color is restored from the stack of the code in procedure. Let's take another look at this code. So in case of return instruction, we are providing the stack for this other level. For call instruction, this is a bit harder. Initial values of stack for previous levels 0, 1 and 2 are kept in the task state segment. We have not set up a task state segment yet. This is something that is needed for task switching. But also, as you can see here, even if we are just going to use a single task, we still need to set up this task segment in order to provide stacks for other levels and make it possible to Colgate to work properly. So to call level 0 from level 3, we need to have a Colgate and a valid task state segment and stack for privilege level 0 set up properly in the task state segment. And then after we execute level 0 code, we can return, and return far is going to restore the previous stack and return back to the color at level 3. Okay, so we still need to look up more things. Task state segment looks like this. So we need to set up stacks here. The rest of the segment may be left uninitialized. This part is written to by CPU when it switches tasks to store off all registers of a task and switch to another one. So at offsets 2 and 4 we need to set up stack for ring 0, and the entire task state should be 44 bytes. First word is 0. This is backlink to another task. We are setting up the same values that are here for the ring 0 stack. And fill it up to 44 bytes. Now let's make a descriptor for this. CSS descriptor. And we need to look up what attributes this descriptor needs to have. And here is something that I already noticed earlier. This says that task state segment descriptor has the lowest bits, either 00001 or 0003. But this is not what is shown here. And also it then said that the limit must be at least 43. What we already have, 44 bytes minimum. The descriptor contains a base address and a limit. But this figure does not have base address nor limit. In fact, if we take a closer look, this is a task gate. We already have attributes for task gate defined. (101). Then this is a mistake in the manual. This is a task gate descriptor. While this should be a TSS descriptor. Back in the day, you needed to be very cautious, because when you had no way of finding and cross-reference this information on the internet, then any mistake in manual could be fatal for you. So many people used to write some notes on the books even when there were mistakes in the books. We should therefore ignore this figure, which is wrong. This is a task gate, not a task descriptor, not a TSS descriptor. We should use this information. Again, this should be present. Present bit should be always set. Privilege level 0. And then bits 1 through 4 should be 3 zeros and 1. So I believe it should be like this then. I'm rearranging a little. Okay, we have a TSS segment and its descriptor set up. Oh, look what I found. Another figure which is set to be task gate contains this task state segment descriptor. So they are just swapped. I think we have a correct layout then. Load task register instruction needs a selector. Oh, is there a mistake in these attributes? No, I think it's okay. It's 3 zeros and 1, and this additional bit is set to 0. Okay, so we are loading task register with a selector of task state segment. This should set up task state segment for us. Well, something's wrong. Let me see, we might have initialized too few values in the task state. But I believe we are already over time for today. So let's go back to this tomorrow and try to finish setting up this task state, and then prepare a Colgate and try to call ring 0 code from ring 3. For now we can disable this. And have our program still running correctly. In ring 3, this message has been written by a code operating in ring 3. Thank you for watching and see you next time.